So I know some of you still are waiting to finish, but I think the vast majority of you managed to finish. So unfortunately, because we have two speeds perhaps, but there will be time to catch up later with Alex and with Sarah, who will stay behind. So don't worry too much if you haven't managed to do it. So you can, it says please clean the filter. That's not on my slides, that's on this Beamer thing. So you can check your solution on that link. It might have solved it in a different way. And also what you will see is that they will have looked at the residuals for the Anova to look at their normality rather than the actual distribution of the variables, because that's another way in which you could assess whether the assumptions are upheld or not. So, moving along. So this is mostly for your reference, because you might come across people writing codes, and in order to understand what they're doing, so don't worry too much about all the symbols. I just have to tell you them because people will come across, you will come across this type of code. So when we add plus, it means adding an explanatory variable. Minus means deleting an explanatory variable. This is interactions or multiplication, so that's star notation. This means nesting, so one is underneath the other one. We'll come to that, and this means conditioning. So, and not or as you have it for this for in the beginning when I talked to you about and or not and all these other things for saving variables. So z is read as y as a function of x given z. Yeah, so that's a conditional expression. So again, don't worry too much about this, but this is the type of formulae that people use when writing these equations. Yeah. So if we want to have like a three-way Anova, so then we would have y as our dependent and then n times p times k, and that's a factorial Anova which will have all the terms and all the lower terms. So we'll have the two-way interactions, and then all the two-way interactions between n times k, n times p, p times k, and then all the main effects. Yeah, so that's a fully blown factorial Anova. If you wanted a three-way Anova, but not the interaction, the three-way interaction, so you want a three-way Anova, but without a three-way interactions, just all the two-way effects and all the main effects, you would drop this term like this. Yeah. So depending on what your supervisor wants, you might want to just have all the two-way interactions without this three-way interaction, or you might also want to have the three-way interaction. So remember that if you're looking for interaction effects, all the lower order effects needs to be in there. So if you're testing a three-way interaction, your model must include all the two-way interactions. If you're testing a two-way interaction, your model must include all the main effects. Yeah. So when you're testing this three-way interaction, all the two-way interactions and all the main effects need to be main defects, main effects. So I'll correct some of these typos when I go through it. So you need all the main effects and all the all the two-way interactions in that model. Yeah. So I'll give you some examples as to how to do it. And as usual, there's more than one way to do it. And I think this is perhaps not the most optimal one. Like last time, you remember that there was easy Anova, and that made it really look nice and pretty. So I focus for most of your thing that you focus on easy Anova because it's most intuitive and most easy to understand. But I'm also going to have to tell you a little bit more about these other ways in which to do it, because again, you might come across somebody else doing it in a separate way, and you have to sort of understand how to also be able to do it in a different way if somebody else wants it in a different way. So this is how I loaded this tooth growth database. I load car because I need this for this Anova command, this capital Anova command. And then if I want to get the same results as SPSS, I have to install these type of contrasts because it changes the options. And then this is how we would do our 2x3 type of Anova, because we have 3 levels of dose and 2 ways in which it's supplemented via ascorbic acid or via vitamin C. So this is just a linear model. This is the Anova in front of it, which will build this F table. And then we just have to tell it also that it needs to use type 3 type of errors. Yeah. And if you do that, you should get close, if not exactly to the same as your supervisor who does it in SPSS or Minitab or MATLAB or whatever he or she uses. Yeah. For a type 3 Anova. So if he's looking at a type 1 sums of squares, then you have to change this to type 1, type 2. So they correspond to these sums of squares that I told you previously about. Yeah? Any questions? So it's something which we've seen before because this is what we used before when making these things. The only thing which has sort of changed is we now have this for this interaction effect rather than the plus for two main effects, which we had before when we were looking at basic Anovas. Okay. Then we make this object, so we can print this object, and these are the type 3 of tests, and they're the F values, and these are the things that you will be looking for in your SPSS output as well, and things you typically report. And we can see here via the star notation that the supplement type dose interaction is significant, yeah, statistically significant, because it's 0.02. We can do it also in an alternative way, yeah. So we can use if we change the contrasts in a very funky way with CAR, we can change this, and then we can have LM. We can have a summary from the LM, then it will print the coefficients. So note that we have the coefficients here rather than the interaction effect, this f-test. And in order to get this f-test, we can use drop 1, and then we can get the f-test, and this is exactly the same value as we had before. So as usual, there's more than one way in R to achieve the same type of thing and get the same type of result, yeah? So mostly this is for your reference, and you might pick the one which you like most because it takes least amount of code, or because you really like the CAR package, or you really like the easy package. But I have to tell you a little bit more about the different ways in which you can calculate them. So remember easy, like it is quite easy. So, but remember that easy needs an ID variable because it calls for that. So we're going to make that. We know there are 60 guinea pigs, and this is just a sequence variable to go from 1 to 60. That will make our ID variable. Then the code is we feed it the data. We tell it which one is the dependent variable. We tell it which one is the ID variable. And then we say these are the between things. And here we don't really have to say, because by default it will do this type of two-way interaction. So we don't have to say multiply or plus or something. It will just by default build a full factorial Anova. Yeah. We ask it to return our analysis of variance, and we ask it to make a detailed analysis, and we say again, it's very important to say which type of sums of scores we want, which we want type 1, type 2, or type 3. Yeah? So that's the code for an easy Anova. And now we will make a list, and then from that list we can call all the objects. So this is easy, and you can see it has an Anova object, it has a Levi's object, it has an analysis of variance object, and all these other things listed in there like a $sign. Yeah. So if you're smart enough, you should remember that this is similar to what we had before, yeah, because it's it's significant at 0.02, and then something like this. This should be closer, if not exactly the same f value that we had before. But the bonus thing is that we also have these f tests for Levi's test again, where it will do this test, and you can say, hopefully, as you also found, there's no violation of homogeneity variance in your set, yeah. So what we can then do is, usually you want to export this and make it look quite nice. So you could do that for the car object, or you could do that for the Anova object from Easy. And again, we're going to use Stargazer. And again, you can further beautify it by changing the labels. You can change anything you want in Stargazer. And this will then give you like an HTML file, which you can then paste into your report. Yeah. So let's have a look at what that looks like. So I will have an easy 2.3 HTML and an Anova 2.3 HTML generated like this. So this is just taking the Anova object from that and turning it into a data frame and then printing that in an HTML format. Let's see what it looks like. So let's see how fast or how slow my browser is. Is it because I'm on the max screen? There we go. So we'll make something like this, yeah? And again, you could change all these labels if you change the names of the variables in your data set, because it's a data set, and so you can change the names and you can make it look like you want it to look, yeah? So again, if you have to do this often, it will save you time, because you can get all these things outputted straight away, yeah? So that's the easy Anova one. Let's have a look at the, not that one, not lecture 4. Too many folders, way too many folders. So perhaps we should just go this way and go here and then go to easy. And so here it's printed this, and this perhaps doesn't make sense, so you perhaps consider dropping a column. And this, just you remember, is this effect size measure, which it will also print if you go down the easy route. Yeah, so the benefit again is like otherwise in SPSS you would copy and paste to Excel or to Word and then spend time tinkering with all the layouts. Here, with relatively easy steps, you can get something which looks like a bearable table, and you can again change all these other labels because it's a data frame. So, and if you have to do that over and over for your thesis, it might save you some time. Okay, so how would you write this up? You would say a two-way ANOVA was conducted to examine the effect of supplement and dose on growth of the odontoblasts. There was a significant interaction effect between supplement and dose. So if you're only interested in this interaction effect, and that's your key hypothesis, you would just report that. Normally, one would also report all the main effects, but it depends on your theory and your hypothesis. So if before you said my hypothesis is about this interaction effect, then you would only report this. You report the F value, then this P value, and then this is the effect size. Yeah. And then you would further explore or plot the results to sort of show where does this interaction effect lie. Yeah. So if you want the post-hoc tests, which your supervisor might also ask, this is the way to get them. So you can get them from the AOV thing. You say the post-hocs for dose, because that's the only one for which it makes sense, because you have 3 levels there. The other one only has 2 levels. So it makes no sense to look at contrast. So, but if you want to find out where the contrast lies, you can get the lower and upper difference between these type of things and the p-values adjusted. The p-values adjusted for multiple testing, for example, there as well. Yeah. So you would find in this case there is a difference. There's differences all the way around, actually. I think. Yeah. Okay. You can also again do it in a very different way. And again, for some of these things, I'll just say this is for your reference. Have a look at it. And so here you could say this is a different way of computing it, and these are 2 key contrasts. And depending on what your supervisor wants, you can get Helmert contrast, Bonferroni contrast, SIDAC, all these other type of contrasts still exist and live in R, depending on what you want. So after this, we should perhaps have a short break. So you can make a plot, and there's something called ggpubr, which will make GG plots for publications and make it slightly easier for you to make plots. And so here I've used this. So it's using GG violin, and then feeding the data set using dose, which you can see here, and then we can say the y variable is the length of these odontoblasts, and then we color by dose. We can pick the palette, so if you don't like black, dark blue, or dark red, you can pick different colors. And we can change the shape also by dose, and then we can wrap it based on supplements. So this is orange juice, and this is the vitamin C ascorbic acid type of thing. Yeah. So in this case, we plotted this way. Yeah. So does that make sense? So just have a look at those type of codes, and so you can make some pretty plots, then demonstrating where the effects are, and you can see hopefully that this is a stronger gradient perhaps in this one than in the other one. Okay. If you want to have the means and standard deviations, there's an easy way to do that as well. So we can ask APA tables to get the 2-way, so we just say it's a 2-way table, supplement dose, length, tooth growth, and then this, and it will give us the means and standard deviations for all these things, and it will also give you, no, it doesn't give you the Cohen's D's, but I'll show you what it looks like. So, did it print it? What's it called? Tooth growth Anova. So, because I didn't change the extension, this is sort of what it will look like. So it'll make a nice little table with like the means and standard deviation, and we'll give you the 95% confidence interval around those means and standard deviations. So, and again, if you change the label so it spells out and says this is orange juice, it will look even prettier. So at this point, I think we should perhaps break for 10 minutes. So I see you back at 12 past to be exact. Don't look at that clock because that clock isn't accurate, but let's have a 10-minute break and then we'll return. And then we're going to look at more other forms of interaction where you have continuous variables.